Greetings. The problem I want to solve today is on the supersonic wind tunnel. Of course, it's the far simplified version of the tunnel, but still, the problem is good enough to teach us about isentropic flow calculations and also about shock waves. Well, this is the general form of a supersonic wind tunnel where it is expected that the tunnel draws air from the atmosphere. It is something at T0 and P0. It might be some condition there, high pressure, different temperature, but for the time being, our tunnel is the one that draws everything from the atmosphere. And then the flow goes into a converging, diverging nozzle, where at the throat, let's call it star, point to star, it reaches sonic velocity. And then at the test section, let's call it 1, it has supersonic velocity. So the problem we talk about now is a circular wind tunnel. So the wind tunnel is a circular, it means that it has a circular cross section, it's a circular wind tunnel, it's a circular wind tunnel, and the diameter at the test section, let's call it D1, equals 0.25 meters, that's 25 centimeters, and the Mach number there is M1 equals 1.8. These are the desired properties of the supersonic wind tunnel. Now, the air that, in fact, is drawn into the wind tunnel, let's say T0 equals 300 kelvins and P0 equals 100 kilo pascals. It is assumed that the tunnel is isentropic. At least before we discuss about the shock wave, the tunnel is isentropic. Therefore, there is no friction. Sgen equals 0 and Q dot equals 0, and it is a steady tunnel. It means that there is a fan at the end of the tunnel where it is continuously drawing air from atmosphere, going through the nozzle, going through the test section, and it is expected, at least ideally, that there is a supersonic diffuser where the flow returns to sonic, returns to the throat at Mach 1, and then continues subsonic. So the exact reverse of what happened in the supersonic nozzle would happen in this supersonic diffuser. We shall discuss later on why such concept is not possible, and it's just only an ideal concept. But for the time being, let's assume that this is possible, and whatever that happens in the nozzle, the reverse of it would happen in the diffuser. So, at least what we have here, we have stagnation conditions in the at the entrance. We know that, and for that knowledge, just for that knowledge of whatever stagnation conditions at the entrance are, we could do some initial calculations that we do now. We are told that at the entrance, the temperature is 300 Kelvin. We could show this to start with on a TS diagram. It's very important to show everything on the TS diagram, as I have done quite often in these videos, and say this is a constant temperature line, and that is 300 Kelvin. Okay, If this is the case, just with this single knowledge, we could calculate the speed of sound at entrance. That is, A0, A0 equals square root of gamma RT 0, and that equals square root of 1.4 times 287 and times 300, and the speed of sound here would be 347.2 meters per second. So we already know that a, a sonic wave, very small wave, very small pressure wave, travels at speed of 347.2 meters per second in the uh, entry air. Velocity is, of course, far from the entrance, and it is v is 0, but a has this value. And therefore, what we could write here on our diagram is that m here, Mach number here, is 0, since the Mach number is velocity over speed of sound, and the speed of sound, it has a value, velocity of the air is 0, and therefore Mach number is 0. At station 1, we're told that the Mach number is 1.8, and also diameter is 0.25. Just the knowledge of one non-dimensional parameter, which is the Mach number here, is good enough for us to be able to calculate or read from tables quite a number of other non-dimensional parameters. And if we move to this figure from, I've selected it from book by Sengel, but there are a lot of books, in almost many thermodynamic books you can find such tables, and all gas dynamics books there are such tables that simplify our work for calculating P over P0, rho over rho 0, and T over T0 as functions of Mach number. You just need to give them the value of Mach number, and they would return these values, and the more important value is A over A star. And what I do now is to select the row for 1.8, where it tells me that the A over A star is 1.4390, P over P0 is 0.1740, and T over T0 is 0.6068. Well, I copied these values on my paper, A over A star, P1 over P star, and P0 and T1 over T0. What do they mean? A1 over A star is the area ratio between this point and the throat. Let's call it 1 star, okay? And P1 over P0 is the ratio between static pressure here and the total pressure here, which happens to be the same as the total pressure here. So P, let's write it in this way, that P01 here equals 100 kilopascal, since the flow is isentropic. And also T01 would also be 300 Kelvin, since the flow is adiabatic. In fact, if we want to show this on our diagram, it's very simple to do that. This is T01, and let's select a line here. This is P01, and therefore this is the point 01. And since the flow is isentropic, what we could do is just to draw an isentropic line here, and this is the line that the flow follows as it goes through the supersonic uh, tunnel. I mean, just as the flow is entering here from stagnation condition, going to Mach 1 and then going to Mach 1.8, in the very similar way, it goes from here, which is a stagnation condition, and goes through all these points. Somewhere along the line, it comes to sonic velocity, which is the throat, which I'll show where it is in a short time. And then it continues to supersonic velocities up until somewhere here, where Mach number would be 1.8, and therefore the exact flow that physically moves along the supersonic wind tunnel here would also move down along the isentropic line here. And so for all these points, the isentropic pressure would be PO1, isentropic stagnation temperature would be the stagnation temperature would be 300 Kelvin, and stagnation pressure would be 100 kilopascal. That is, these are the values. Okay, now let's start with these values here, and let's give them some meaning. What do they mean? Okay, from here we conclude that T1 equals T1 equals T0 times this value. So it is 0.6068 times 300. And the outcome would be for T1 would be 182.04 Kelvin. Okay, this is the value for static temperature at the test section. Let's see what this means on our TS diagram. It means that there is a point at T1 equals 182.04, which would be, say, somewhere here. This is the constant temperature line where the temperature is 182.04. And here M equals 1.8 for isentropic flow. In fact, we haven't used much for isentropic values. It's enough if the flow is adiabatic, and this idea would remain the same up to here. I mean, the total, as long as total temperature is 300, Mach number is 1.8, and static pressure is 182. These values match. Pressures here where isentropicity, being isentropic, would come into play. But for temperatures, being adiabatic would do. Okay. Now, one more knowledge that we can calculate just from here is the velocity at point 1. V1, you see, for the total temperature, we know that TO equals T plus V squared over 2 CP0. From this equation, V squared would be 2 times CP0, which for air it is 1004.5 times T0, which was 300, and T, which is 182.04. And the outcome is that V1 is equal 486.81 meters per second. This is the value for V1, and we could also show this on the TS diagram, and this distance here, this distance is this difference between T01 and T1, and it is V squared. Let's put it here, V squared, V1 squared over 2CP. 0, exactly, since it's the difference between TO and T. Just very similar to the case that we were able to calculate the speed of sound, just from knowledge of the total temperature at the stagnation conditions, or at the outside before the tunnel entrance. With the knowledge of T1, we are able to calculate the speed of sound at the test section. What we do is that A1 equals root square gamma RT1, and that equals square root of 1.4 times 287, and this time times 182.04, and the speed of sound A1 would be 270.4 meters per second. And that's the speed of sound for station at station 1. Just to check to see if everything matches, we could write that M1 should equal V1 over A1, and the V1 we calculated was 486.81, and A1 we calculated was 270.4, and that equals 1.8. So all our calculations up to here are correct and match. Now, let's return to our previous page here. And another knowledge that we had was over P1 over P0. And let's see if we can calculate and learn P1. You see, P1 is the pressure at point 1. This is the line where T equals T1. Let's call it T1 equals, and the pressure here would be P1. And you could easily calculate it from isentropic relation between O1 and 1. And also this equation gives us exactly the same answer because it's the same thing. So what we do is that P1 from here, P1, you conclude that P1 equals P0, which is 100 times this value, which is 0.1740, and therefore P1 would be 17.40 kilo Pascal. Well, show it here, and therefore the value for this constant pressure line is P1 equals 70.40 kilo Pascal. This is the 100 kilopascal line, and this is 17.40 kilopascal line. Now, up until now, for point 1, we know P0, T0, V, A, P1, and T1. So we have almost all information we need about point 1. And since we also have the diameter, we could calculate mass flow rate at point 1. And that's what I'm going to do now. M dot as point 1 equals M dot 1 equals rho AV, and that is P1 over R T1 times A1, which is P D1 squared over 4, and times V1. We have all the knowledge we require, and therefore it equals 17.40 divided by 0.287 times 182.04. Please note that all these values are static values, stagnation values, or stagnation properties at point 1, but still for all calculations, we need the static values. For the speed of sound, we use static value, and for mass flow rate, we use static values times P times 0.25 squared divided by 4 and times 486.81 meters per second, and therefore mass flow rate at 1 would be 7.961 kilograms per second. This is the mass flow rate at point 1, and as you can see, this mass flow rate remains the same throughout the tunnel. Throughout the tunnel, mass flow rate would be the same because no mass enters from the sides, and all mass that enters leaves. So it's a control volume that whatever that enters also leaves the section. So however you select your control volume, the mass flow rate would remain the same. It's also a good idea to put all these various numbers in it, and therefore we have a consistent way of presenting different data that we have calculated and presented them in different equations. At point 01, which was our stagnation conditions, we knew pressure and temperature. That was what was given us to start with. The diameter would be meaningless since Mach number and velocity are both 0, and when there is no velocity, it means that we have selected the largest possible area where the Mach number or velocity is negligible. So diameter here would be meaningless. Speed of sound at 0.01, we calculated it, and that it is 347.2, and M dot would be the same as we have calculated. We couldn't point it here because we have to say M dot equals rho A V. And what we have done is we have assumed A to be infinity, V to be 0, and therefore it's ambiguous multiplication. We have the value somewhere else, but there's no point in presenting it here. Now, pressure at point 1, static pressure and temperature, where we calculated it. We know what are static pressure. Temperatures are diameter. We were given at the start of the problem to be 0.25 meters. Mach number we knew it to be 1.8. We calculated the velocity and speed of sound uh, 486.81 and 270. And if you remember, we divided them and learned that the ratio is the ratio of Mach number is 1.8. The mass flow rate, we just calculated it, and it was 7.961. Our next step would be to move to the first throat. That means here, and see what the properties at the first throat are. And I shall continue this problem in my next video. Thanks for watching, and cheers.